All right, let's talk about Newton's law of cooling. So with this formula, what we have is big T of little t equals A times E raised to the K times T plus T sub S. So it feels like there's a lot going on in this formula. Don't get intimidated by this. Let's break it down. So T of T is telling us this is a function where little t is our variable that's getting plugged in. And what this represents is the temperature of some object over time, little t. Now, A is going to be some difference between initial temperature of the object and the surroundings. So that's just going to be some constant. We'll find that along the way. K is going to be the continuous rate of cooling. And so it's just going to be some constant also, and it's going to be the rate. T sub S is going to be the surrounding temperature. The surrounding air temperature. So it could be the room temperature if you've placed the object in a regular room, could be the temperature of the refrigerator, something like that. But if we break this down even further, taking a look at this formula, what we have is this is an exponential function. Our variable is up here in the exponent, and it's basically been shifted. So this is going to be a vertical shift. A is going to be some sort of stretch or compression. It's just a constant, and R is our rate. So we've dealt with this type of formula before. Don't be intimidated by it. We'll walk through an example here and show you exactly how this goes. They're kind of involved examples, but we can work it one step at a time. All right, let's take a look real quickly though at what's going on with this graph. Because sometimes that's handy to kind of visualize what's going on. So what we have is we have something's been taken out of, say, an oven. And so we know its initial temperature is going to be given. We know how hot it is as it's come out of the oven. And then initially what happens is you take it out and it starts cooling off pretty quickly. But then that gets continues getting cooler and cooler and cooler. It's just not as quickly as we move over our time. Eventually, though, it is going to get close to the surrounding temperature. So whether that be room temperature or whatever it is, if we have T sub S, it's going to get very close there to some horizontal asymptote. So that's what we think of as what's going on. Now, this formula actually does work if things are getting hotter over time, but we've called it Newton's law of cooling because we're thinking about things getting cooler over time. And of course, this would be initial amount right here as we're taking it out of the oven, that'd be at like times 0. So we don't think about the rest of this graph, thinking about some exponential function would be going up this direction, but we leave that off because we start our time at times 0. All right, let's take a look at a cheesecake example. So cheesecake is taken out of the oven with an ideal internal temperature of 165 degrees Fahrenheit. And then it's placed in a 35-degree Fahrenheit refrigerator. After 10 minutes, the cheesecake is cooled to 150 degrees Fahrenheit. Now we're going to have to wait until it has cooled to 70 degrees Fahrenheit before we can eat it. How long do we have to wait? Feels a little overwhelming when you first read through these. There's a lot going on, but let's break it down that we actually are given 3 key pieces of information before we answer that question about 70 degrees Fahrenheit. So 3 pieces of information I know of are the initial temperature was 165 degrees when we took it out. So each one of our ordered pairs, and we're given 2 here, have to do with like a time, that was our input, and then the temperature of the object at that time. So the first one is when we first take it out, that's at time 0, we know the temperature was 165 degrees. The next piece of information as we read through this is it was placed into a 35-degree Fahrenheit refrigerator. So that's the temperature of the surrounding air. So T sub S is going to be 35 for the rest of this problem. The third piece of information is actually another ordered pair. After 10 minutes, the cheesecake is cooled to 150 degrees Fahrenheit. So if I put that as time, 10 minutes, then 150 degrees was our temperature. Remember, it goes T, time, then big T, temperature. Let's start out with this first piece of information though. The initial temperature was 165, and let's put that with our T sub S. try to plug all of this in. So remember that was 0, 165 goes along with 165 is going to go for our temperature, equals A, we don't know, e raised to the k times 0 power, that was our time, plus 35, T sub s. So now it does kind of feel like we have two unknowns. We don't know A, we don't know K, but look, because we have 0 being multiplied by K, that's just going to become 0. So we have 165 equals A, e raised to the 0 power plus 35, and we only have one unknown. We don't know what A is because E is a number. So let's go ahead and subtract 35 from both sides. Our goal here being solve for A. So we have 130 equals A times, well, e to the 0 power, anything to the 0 power is going to be 1. So we can say A has to be 130. And A is going to be this constant. It's going to be 130 for the rest of this. So kind of outlining exactly what we know that this is going to be the same the rest of the way through. And then we know A is going to be 130 the rest of the way through. Well, what information haven't we used yet? We haven't used this other ordered pair that we found, right? 10, 150. So let's try plugging that in using the other information that we know. So remember, that's going to be 150 goes on the left side, it's a temperature, and 10 is going to go in for little t. So 150 goes on the left side equals 130 e raised to the k times 10 plus 35. Double check there. 150 went in for our temperature on the left side. 130 was A that we found in that previous step. E raised to the k times our time of 10. All right, now let's see if we can solve this down. So exponential equation, we have k's are unknown up in the exponent. Let's go ahead and try to isolate that exponential part. So let's subtract 35 from both sides. Move that away. So we have 150 minus 150 minus 35 is 115 equals 130 e raised to the 10k. I switched the order there, but they're being multiplied, so that doesn't really matter. All right, let's get rid of the 130 next. So divide by 130. So I know that 115 divided by 130 can reduce down further. I'm just not going to bother with it right now. All right, next up, we have a e raised to the power. So that e is kind of a good indicator. We want to use a natural log on both sides. So natural log of 115 over 130 equals natural log of e raised to the 10k. And because we use the natural log and e was the base, we're going to get really nice canceling out on the right side and get 10k left over. Just left with the exponent, 115 over 130. And finally, to get k by itself, we just divide both sides by 10. So we now know that k has to equal, it looks weird, but this is a nice exact answer that what we have here. Natural log of 115 divided by 130, all divided by 10. So as we put all that information together, we actually end up with the function. So I'm going to take all this information, put it together into a nice function. Let's go with t of t equals a is 130, e raised to the, I know it looks weird, natural log of 115 over 130 divided by 10 times t plus 35. So if all we were asked to do was come up with the function itself, and all of this is in the exponent, that would be our function. We were asked to go an extra step on this one though. Remember that we are not allowed to eat this cheesecake until it is only 70 degrees Fahrenheit. So we have a follow-up problem on this one. You won't always have follow-up problems. Sometimes you're just going to be asked for the function itself. But let's see if we can answer this follow-up question. So in this case, our follow-up has to do with a temperature of 70 degrees. So what I'm going to do is I'm going to take that 70 degrees, use the function we just created, and I'm going to plug that into the left-hand side and do some solving down. So let's go down here. We said 70 degrees goes in for our temperature. So we have 70 equals 130 e raised to the natural log of 115 over 130 divided by 10 times t with a plus 35 out here. So let's work some steps together and solve this down for little t, our only unknown. So let's subtract 35. These go away. 70 minus 35 is 35 equals 130 e raised to the natural log of 115 over 130. And I know this is a very involved problem. That's why I wanted to do it together, though, just to make sure you see all these steps. All right, next up, we want to isolate the e to the power. And all of this is up in the exponent. So let's divide by 130. These 130s will go away. So we end up with 35 over 130 equals e raised to the natural log of 115 over 130 all over 10 times t. E to a power, let's use a natural log on both sides. So we go natural log of 35 over 130 equals the natural log of all of this. And that's going to do some very nice canceling out, where natural log and the e get to cancel. So we're just left with the exponent. Natural log of 35 over 130, bringing that down, equals just the exponent, natural log of 115 over 130 divided by 10 times t. And now I would probably do it as two steps because why not? Let's multiply to get rid of that fraction. So that goes away. And if you're okay visualizing this, I'm going to just divide by that natural log because t is connected with that natural log with multiplication. So I'm going to divide both sides by natural log of 115 over 130 on both sides. Therefore, these get to cancel. We have t all by itself. We have an exact answer. And let's go ahead and punch this in and see how long it is going to take to finally get to eat this cheesecake. So we have 10 multiplied by natural log of 35 divided by 130, close some parentheses, divide by, again, natural log button, 115 divided by 130, close some more parentheses. I got 107 approximately. And I guess that's in minutes, approximately equal to t. Because our original value is the 10 minutes, we knew the internal temperature after 10 minutes, so our time t is in minutes. So how long is that really? That is, what, at 1 hour and 47 minutes? Yay. All right, so it is a long process. Not to belittle the point, there's a lot going on in these that you just need to take your time, go one step at a time. I think if you look at this one in the book, they go ahead and after they find K, they don't leave K in this exact form. What they do instead is they do get an approximation, which you want to be careful of if you do approximate your rate at any point, and we really don't like to, unless it's a very long problem like this, is if you truncate your non-terminating decimal at some place, it's going to affect your overall answer, and it could mess with that. Maybe that doesn't matter too much when you're eating a cheesecake, but in general, keeping exact rates is a very good idea. So anyway, enjoyed putting this together. I really hope this helps you out as you're trying to figure out Newton's law of cooling. Anyway, if you want to subscribe, go ahead. If not, that's okay too, I suppose. Till next time.